Okay, sound is working. And here, Tech, we don't have enough bandwidth, do we? Hey. This is so slow anymore. Let's see. And let's see if this changes. This is just slow compared to how this used to work. That's bad. Okay, let's go to the dashboard. Oh, I have so many steps just to do so little. This is just there we go. Let's test that. Yeah, very good. Okay. Okay, y'all, I think we're good to go here. Give me just a second. I'll get everything else set up. If you're watching live, welcome. And if not, and you watch this later, please make sure that you ask any questions about anything that I presented. And let's get everything up and running really quick here. I think with the people that we have in this course, we can kind of move through stuff a little bit quicker. And kind of what I would like to do with some of this is maybe have you all work past what we usually get through in this course. And then we can spend the last couple of weeks of the course doing some things, some statistical and analytic techniques that would actually, real world analytic techniques for IO psychologists. Anyway, let me get the room set up. We adjust this. There we go. That works. We'll start off with the syllabus. I can find the syllabus. Okay, it looks like the syllabus failed to load, so we'll go right to the presentation part. With the syllabus, a couple of things I want to note in there. We're probably not going to stick to the syllabus as it's written. What I'm going to try to do is, since we only have 3 people in here, is try to accommodate everybody's different needs in terms of what you need to get out of this course. And we'll also talk a little bit about where you see yourself going professionally after you graduate, and think in terms of what would be some good statistical or data analytic or program evaluation or other types of techniques that you could get from this class. The other thing I'll mention before we get into the presentation here is that I have a link for software package in the syllabus, and it's for a program called JASP. And kind of a way to think about JASP is this is going to be like free SPSS. It's shareware. It's got just a list of really good people involved with the development of this, including Andy Field. If you've read anything about statistics, or who's kind of leading the way with statistics and statistical education for the social sciences, Andy Fields is one of the big names, and a lot of people just refer to him as the stat book guy. So him and probably a few hundred other people have been working on this, and what this will give you is give you most of the stuff that we would end up using in SPSS for free. It runs just as fast as SPSS. You can also load this on tablets or iPhones, wherever you feel like running it. With respect to the stuff that we're going to be covering in here, the t-test, ANOVA, correlation, we'll get into some multivariate, multiple regression stuff too. This is all going to be in this package. Again, how can you argue with free? Now, the drawback with this is that it doesn't have a good data editor in it. Like, okay, if you've been working with SPSS, you have that variable view page and the data view page. This is not going to have the variable, or I'm sorry, the data view page. So what you're going to have to do is you'll have to edit the data in Excel or some other application where you can do either a spreadsheet or comma delimited file, and then pull it into JASP. Now, if you have data sets that were created in SPSS, this will pull them right in seamlessly. In other words, you can actually use the two packages to talk back and forth, or, well, let me be more specific about that. You can exchange the files seamlessly. I've tried this a number of times, even with complicated stuff. Now, if you put something together with SPSS, one thing you'll have to do is put a header row on top of that file to just list what the variables are. We'll get into that hopefully next week with this program. In the meantime, get this application, download it. There's some good tutorials on YouTube and even some good built-in tutorials with this. I think this is one of the coolest things I've seen in a long time, other than R, but the advantages to this versus R is this is going to have windows. Okay? So this is going to be menu-driven. Versus R, you have to know how to code or have to learn how to code. So any questions about that, contact me during the week, and if you have any trouble getting started with it, I'll be glad to help you. So the presentation for tonight. Got a fairly sizable slide deck here. We'll get started with some of the ideas and some of the concepts. I know with two of you, you had undergraduate statistics with me. So again, one of the reasons why we'll kind of work off syllabus and we'll kind of push ahead with this is I know what you're capable of. I know that you already have a pretty decent facility with statistics, and I don't want to slow you down. I want to try as much as possible to get you up to speed so that you get that first professional IO job and you're able to hit the ground running with something significant with respect to statistics and analysis. So statistics, why do we use statistics? You want to Google something really interesting, look at the history on some of this stuff and how far it actually goes back. The modern statistics, in terms of what we do with descriptive statistics and inferential statistics, testing incidence probability, that goes back into the 17th century. And the big leaps, I think, were made probably middle 20th century, not because we did anything more with math than we were previously doing, but because we started to have the availability of computers. And as that technology kind of increased in power and availability, it's made a big difference in terms of people, worldwide being able to use statistics and being able to use numbers to make some kind of data drawn a database decision versus intuitive decisions. So mathematics describe and depict our findings. We draw conclusions from our results. We test hypotheses. We test to see relationships among variables. And if you had correlation regression before, you talked about does one variable increase or decrease, that is the amount of something increase or decrease, the presence of something else increasing or decreasing. With the testing of hypotheses, kind of the bottom line there, if you want to summarize that in plain English, is that we're going to take a look at a pattern of numbers, or perhaps two or more patterns of numbers. And we're going to look at those two patterns and we're going to say, okay, are these basically the same on the basis of what we know about random fluctuation, or is something different going on here? Is something other than random fluctuation going on? Is there something where we can say, okay, we see this difference here, and we think this difference isn't just random fluctuation, but it's being caused by it, and then come up with some kind of relationship, or some kind of variable we control with such things. Hopefully, this is kind of review here. Numerical data can be descriptive. So one of the things I'm going to throw out is somebody asks you what descriptive statistics are. If you're going to adhere to the rules that dictionaries do, you can't use some variation of the word to define the term. In other words, what are descriptive statistics? Well, you can't just go ahead and say they describe a set of numbers. A better way of saying that without using some variation of description is to say that they summarize and characterize a group of numbers. So census data, Bureau of Labor Statistics data, I mean, those would be examples of, okay, we counted different variables within the population, and this is how we think this population looks if we talk by proportion or relative amounts. Inferential statistics. Well, how much confidence do we have that something could generalize from the sample to the population? Or we'll get into playing around with this a little bit more detail, because this tends to be kind of but it's not a real difficult concept, but you have to think about it and picture before it makes a whole lot of sense. So if we say population, we're testing to see if two samples come from the population. Basically what we're doing is we're estimating what the bigger population would look like if it had those two groups in it, and determining whether those two samples came out of that population. So the two samples come out of a bigger population, or sometimes we just go sample to sample. We look at how the numbers are spread on some variable, or how they're scattered on some variable within sample one, and based on what we know about general random probability, we make some kind of calculation in terms of what do we think is the probability of those two samples being the same, or what's the probability of them being different. Now, if you recall, alpha levels, 0.05. The bottom line there was not that you were saying that anything was scientifically proven, but you were saying that there was only a 5% probability that whatever you said was causing the difference, or even if there was a difference, only 5% probability that it's not a difference. And if you had undergraduate stat class, an undergraduate stat class would mean one of the things I mentioned is that science ultimately proves nothing. And I might have also gotten on a little bit of a rant about, you watch commercials on television, and sometimes they'll advertise some kind of product as being scientifically proven. Well, science doesn't present proofs. What science does is gives you clues in terms of which is most likely to be true based on determining which explanation or which relationship among variables seems to have the lowest probability of being random. So, yeah. Should have edited this up a little bit, right? Powerful tools or superpowers, must use them for good. One of the things we'll talk about in here is cleaning data, and also making sure that the data are going to represent some kind of population, make sure that the data is going to be valid and reliable. We'll review the concept of internal and external validity with some of the work that we're going to do in here. External validity is the idea that whatever you found in some numbers applies to a whole population, applies back to a group of people that you think sample represented. Internal validity comes down to, are you measuring what you say you're measuring? And in the social sciences, we have a lot of problems with demonstrating and measuring what we say we're measuring. Among other things, we're a soft science. We're not like physics or chemistry. We're not looking directly at whatever it is we say we're studying or we're researching. What we're doing is a lot of times we're looking at constructs. So if you had a class with Jerry Kabachik, you talked about the neo, or you talked about personality variables, personality traits. Those traits are constructs. So for example, if you were talking about something like introversion, extroversion, you're not looking directly at introversion, extroversion. What you're doing is you're looking at a set of behaviors that you think can be attributed to, somebody being relatively introverted or relatively extroverted. Same thing with conscientiousness. You can't look directly at conscientiousness, but you see behaviors that make you say, okay, this person is more conscientious than this other person. And it works the same way with just about everything you can study in psychology, unless you're going the Skinnerian route. We might have a little fun with Skinner and behavioral methods, probably about 3/4 of the way through summer. But if you're in clinical psychology, you're not looking directly at depression or anxiety disorders or bipolar disorder, schizophrenia. What you're looking at and what you're measuring in terms of the stuff that we do, you're looking at behaviors and say, okay, this person behaves this way because they're depressed, or they're anxious, or they have schizophrenia, or any one of thousands of other different individual different characteristics. For those of you that are going into training and development, one of the things that will typically get measured when people are trying to determine whether or not a training program is going to do any good is they'll measure something called readiness for training. Again, a construct. You're not looking directly at readiness for training, but you're gathering some kind of other behavioral sample, perhaps some kind of test or questionnaire to determine whether or not a group of people is or is not ready for training. Have the right type of data, have statistical techniques that are applied appropriately. I think one of the controversies that has occurred within the last 5 to 10 years is whether the statistics that we're using a lot, based on the idea that the data we're gathering, if plotted, will produce a bell curve. I think we're doing a lot of research where that assumption isn't quite the case. If you're in IO psychology, a lot of times, if you're looking at test and testing data, or you're measuring differences in performance, you're going to have what are called left skew distributions. That is, more people are going to be piled up on the high end of whatever it is you're measuring. So one of the discussions we'll have one of these nights is, are we using the appropriate statistical tests? Are we violating assumptions? If so, is it okay that we violated assumptions a little bit? How do we decide when you've gone too far with respect to violating assumptions? And if assumptions are completely violated, what do you do next? Results are interpreted correctly. Yeah. What was the line that sometimes get attributed to Mark Twain? There are 3 types of lies: damn lies, damn lies, and statistics. I'm going to, if you haven't heard me say this before, I'm going to say that statistics don't lie. But the bottom line is statistics are numbers. And the lie, if it's going to happen, is going to occur because of the interpretation. Okay? So that last point, numbers may not lie, but people can. Or people can twist the numbers to make it look like they're making a solid argument for something for which they're not. Sometimes people just flat out make mistakes when they're interpreting statistics and numbers. So, give you an example of how that would happen, or how the interpretation could throw things off a little bit. So, Tobacco Industry Research Center, excellent health statistics. Smokers are less likely to die of age-related illnesses. Okay? No, that's kind of true. If you look at any of the historic data, especially going back in the 50s to the 80s, if you want to pull any of that up, regular cigarette smoking on average cut off somewhere between 12 to 14 years off of people's lives. So consequently, yeah, good news. The smokers or smoking tobacco is going to keep you from dying of age-related illnesses. I think the other interesting aspect of that is, if you look at what's happening with longevity and how long people are living now, is that a lot of people we're having an increasing number of people come down with dementia. And some people will pull that out and say, oh, look at this, the prevalence of Alzheimer's disease is about 5 times what it was 20 or 25 years ago. And if you back up on that, start taking a look at what else is happening. There's more people living past age 85 or living into their 90s or 100s. So consequently, something like that is going to happen. It's going to happen. So, sometimes when you're making interpretations of what's in the data, you have to consider other data to put it out. Anyway, statistics depends on our sampling method, probability or non-probability. Is it random or is it not random? Now, one of the things I can tell you as somebody who's done quite a bit of research on campus is we do a lot of this non-probability type sampling. Now, what that means is that when I recruit people to participate in my research, it isn't a perfect random sample of the population. I've got a high proportion of higher cognitively functioning, healthier people between 18 and 23. And the other thing I can say about tech is that population is going to be largely a white population. And you can back up on that and say, okay, well, if you're going to apply these results to the state of Louisiana or East Texas or wherever, one of the things that's going to be missing from that sample, obviously, is going to be the age range. And again, you've got a higher cognitive functioning, better, or healthier population. And then, if you look at the demographics here, what are we like? I think in Ruston, we're 49% white, 47% African American, 2% Hispanic Latino, and then whatever makes up the rest of that. The other thing that's kind of interesting about this area and Monroe is that we've got a relatively high population of people who are either immigrants from India or people whose parents were immigrants from India. It makes kind of for an interesting population. But anyway, the idea is that if we gather a sample on campus, it's not going to represent all that. Now, probability sample, perfectly random sample. As far as I know, the only way to get a perfectly random sample of the population, and let's see, you get this past the Institutional Review Board, would be to drive around with that windowless panel van with a group of your friends, a bottle of ether, and abduct people off the street. Other than that, you're not really going to get a true random sample. So, what do we do about this? Do we not do the research? No, but we're dealing with non-probability samples, and we're going to report all this. We acknowledge this as a limitation. If you've had any contact with Jeff Walsick and his lie detection research, majority of his subjects are going to be traditional aged college students. Now, with what he's looking at, kind of what he's hoping for with respect to generalizing his findings is to say that what he's studying is biologically based or it's hardwired in people, so it isn't going to be that much different if we start saying that, okay, we think these results apply to 3-year-olds, we also think they apply to people 103. Even with probability statistics, there's a possibility that statistics, say that 3 times fast, it's like do not accurately reflect the population. That's going to be just about every sample I've ever taken on this campus when I've been working on just strictly theoretical research. Now, in organizations, if you've had contact with me or Tillman and seen some of our research, we go into organizations, we're analyzing things. We probably did represent the population if the population was only supposed to be, or only supposed to generalize that organization. If you talk to Mitzi DeSells or Stephen Toddy about their research, organizational side stuff, measuring things like organizational climate, motivation, things like that. Again, this idea that, okay, this probably wouldn't be real perfect data to say that this applies to the whole population, but it's going to be sufficient to say, okay, this applies back to this workplace. Sampling error, inadequate sampling frame. In other words, we're not taking into account all those things we need to consider to include or have a good representative population, representation of the population, low response rate, coverage. Some people, some populations not given a chance at selection. Now, low response rate, the one thing I can tell you right now, if you're dealing with anything involving survey research, this is going to happen. When I was an undergraduate and when I was a young graduate assistant years ago at Auburn, the internet, well, by the time I was in my second year at Auburn, We finally had internet access. It was mainframe access. It looks nothing like the internet we have now, but it was still a way to get stuff out to people. But not everybody was connected. So there was probably a period between 1991 and 2000 where a lot of mail-out surveys were sent to people. So you send a letter out with a self-addressed stamped returned envelope, and if you're lucky, maybe you would get a 15 or 20% response rate. Well, the problem with that is you don't know that that 15 or 20% of people who actually responded isn't somehow different or a completely different population than the whole population you're trying to sample. So would they be a specialized subgroup of that population? We still deal with this when we're gathering online samples. But one thing I can tell you, for anybody that wants to do some kind of online research, if you've got the funding, you can use Amazon's MTurk, or you can actually use Qualtrics, and both of these platforms have people who have participated previously, and they've got algorithms to check the responses to make sure that it's a good representative sample and that people are being genuine with those responses. Non-sampling errors. Okay, sampling errors. The right population, and also if the sample isn't large enough, one outlier, a couple outliers in one direction can throw everything off. Non-sampling error, things that happen when you're trying to do the measures. Problems with transcribing and coding data. So if you're doing something where you have an open-ended survey and you're asking people to describe how they feel about the economy, about the state of affairs in the world or whatever, you might have to sit down and say, okay, we've got 3,000 responses here. Let's see if we can find a pattern. So we'll look through these, see if we can find them in things that would suggest groupings, and then we'll count by groupings. Well, you could have had all the categories. You could have missed a category. All sorts of things happen when we have human beings interpreting the data. Likewise, if we have observers. And an example of observing doesn't really come up that often in IO psychology, but if somebody was, let's say, evaluating assessment exercises, and they did something called a leaderless group exercise to look for the emergent leader, you have human instrumentation that's trying to determine who's doing what. With a structural interview, same thing. We have human beings that are trying to apply a set of standards, listening to somebody address a structured set of questions. But we can have errors with that. Some types of tests, errors. Give you a quick example here, instrument error. You've all taken lots and lots of tests that were flawed somehow. So for example, you take that midterm test or that final test, and think about this. Did that test include everything that you had covered within that period? And the answer is probably going to be no, because those tests have to be somewhat shorter, have to basically be able to capture a lot of individual differences in understanding content in a very limited time. Let me stop right there. I'll give you a little bit more specific example of that. With any kind of a testing process, we're taking a small sample to infer what happens with a bigger sample. Blood test, we take a small sample of blood, we measure it, determine what's happening with the blood in the body. Same kind of principle applies to tests. We take a small set of questions to determine how well you mastered or learned the material that was presented in class or the readers. And I can guarantee that there's no perfect way to cover everything on a test that was covered during 3 or 4 weeks of a class, unless of course we make them an all-day test. Something we're not working with. So instrument error, or in some cases, are we even using the right instrument? I've seen people use cognitive ability tests to try to determine who's likely to succeed as a manager or a leader or a supervisor. Now, if you had class with Tillman will tell you that cognitive tests are the single best, most consistent predictor we have, which is true. The problem with using them in situations where you're trying to determine who's likely to emerge as a leader is that we've kind of noticed in recent years that the ability to predict leadership falls off at about Z equals 2, or if you're dealing with the Wechsler Adult Intelligence Scale, about an IQ of 1/3. Okay, this should be some good review. Also important to back up and look at this stuff from time to time. So levels of measurement, the relationship among the values assigned to a variable, and the characteristics or attributes of that variable. What I'm going to ask you to do in this class is make sure that you understand each one of these levels, plus understand how the next level relates to the previous level. So this looks pretty familiar: nominal, ordinal, interval, and ratio. And if you had class with me before, you know, one of the things I say about nominal is just take a look at the root word there. It's the Latin word for name. Or if you had a literature class, if you have something like English Lit, 1850 to 1947 or something like that, you might have heard the term nom de plume, which is French for pen name. So anyway, we're talking about naming, or we're talking about categorizing things. Now, ordinal rank order, we can put things in order from least to most, weakest to strongest, greatest, etc. But we don't know the differences between any of those levels. So we can say, in terms of building on this, with ordinal, we have those categories, but we also have something called magnitude. So we have order of magnitude with ordinal. Then interval. What happens with interval is that we try to set equal appearing values. I'm going to say equal appearing values because, if you're looking at something like an IQ scale, it has, scaled out from 0 to 210 points, but the differences between points doesn't always mean the same thing. Or it doesn't exist, it exists in a way where we can compare people based on the scales, based on how those scores are distributed in the population. But we can't make statements like, okay, the person with an IQ of 140 is twice as smart as the person with an IQ of 70. With most of the stuff that we measure in the social sciences, in business and industry, in just about any kind of applied area involving people, it's going to be those kinds of scales. Now, with the ratio scales, we have those equal intervals and an absolute zero. In other words, that puts us in a position to say that something is twice as big as something else. Okay, so give you an example. Height. A person who's 72 inches tall is literally twice as high as somebody who's 36 inches tall. Same thing with weight. Somebody who's 200 pounds is twice as heavy as somebody who's 100 pounds. Now, where this gets a little bit tricky is if I ask about shoe size. So think about this for a minute. Your shoe size interval or ratio? And the answer to that is it's going to be interval, because there's no such thing as a shoe size of 0. And if you ever look at a shoe chart or look at any of those devices that they use to measure feet, size 9 is not literally twice as long as size 4.5, right? So trick question there. Temperature, if we're measuring temperature in Fahrenheit or centigrade, those are going to be interval scales. There's no true 0 there. The 0 on the centigrade scale corresponds to the point at which water freezes, and each one of those centigrade units applies to how many calories it takes to heat 1 cubic centimeter of water. I think it's like 6 calories to heat 1 cubic centimeter of water up 1 degree. But in terms of any kind of a scale that measures temperature that would have a 0, that would be the Kelvin scale, the one used in physics. And with the Kelvin scale, 0 indicates the absolute absence of heat. That is, molecules are not vibrating. Basically, what you have is just a solid mass where nothing is moving. Doesn't quite happen on Earth, but when you get out in the, let's say, out in space someplace, you could probably find some region where you could identify that it has a Kelvin temperature of 0. Anyway, kind of show how this builds. Nominal. The only attribute is going to be the name, the category. There's nothing different about any of the categories. The only thing with the categories is one category A is not category B. So they have to be mutually exclusive, but we're not saying that one category is better than another category. We're just going to say they're mutually exclusive and different. In other words, historically, when we categorized genders, male and female, those were nominal categories. Ordinal, well, we can put things in some kind of, we can rank them by magnitude, greatest to the least. We still have the categories, but we can rank from greatest to least. Now, one exception to that is in some cases when there's tie scores, sometimes people just say, okay, everybody that achieved a certain level that indicates fourth place will be put in fourth place. Sometimes people will split the differences. So if you had two people that, were between 3 and 5, you might split the difference based on how many people were within that interval. Yeah, most of the time we're not going to have to do anything like that in industrial organizational psych. Interval, well, the distance becomes meaningful. Now, back up on this one. Why is the distance unmeaningful with ordinal scales? And the bottom line with that is, well, here, take a look at some kind of Olympic event, something involving running. The 50 meter or the 1,000 meter or, marathon. You can have people come in first, second, third, and fourth, but if you've ever watched in these races, the people that come in like first, second, third, there's maybe tenths or hundreds of seconds between the difference. In other words, it isn't anything that's maybe a meaningful difference, but to apply some kind of fair rule, we decide that, okay, this person that came in 0.2 of a second ahead of this other person gets to be first. And likewise, the differences between, let's say, 5th and 6th places, those intervals become, the actual sizes of the differences become bigger. Well, we're not dealing with that kind of a level of measurement. Okay. Interval, that's where those distances become meaningful. So IQ test. The points mean something, but again, we can't say that they mean something in terms of how we could say, we could define proportions. It just means something in terms of each scale point corresponds to something, and we do it's going to be equal. And then ratio, again, absolute 0. Now, the times when you're going to be dealing with ratio scales in applied IO psychology is when you're counting things like the frequency of the behavior occurring and making statements about this person did the right thing 25% of the time, but this other person did the right thing 50% of the time. So, nominal levels of measurement, categorizing identity. If you look at what's happening here, we've taken age and we've put age into 4 different groups. Now, chances are a better way of doing that would be to just have people report numbers, but sometimes you're going to have strength in numbers, and that's why you would group people by age within categories. Gender, male, female, and we could add on to that. I understand that the whole area of gender psychology has gotten a little bit more complex. Presumably not because anything has really changed with populations, but social norms have allowed people, for example, that whose gender identity might not fit in one category or the other, or the gender identity fits into the opposite category of what they were born with. So we have those kind of categories. I think one of the fun, occasion where somebody pointed this out was kind of funny was when I was working with Southern Natural Gas down in a place called Toka down in St. Bernard's Parish. We're doing job analysis, and I made the statement to the subject matter experts that, as far as I knew, that gender was the only truly dichotomous variable we had. And one of the subject matter experts said to me, well, let's see what you say later. So after we got done with the work and we all headed north, went to New Orleans, went to Bourbon Street for the night, that same subject matter expert said, so Frank, are you still sure that gender is a dichotomous variable? I thought that was a really funny example. I appreciated that one for saying. Okay, level of agreement. Well, if you've seen this with the Likert scale, right? Now, this is where it gets kind of interesting with stuff that we do, is that Likert scale, if you think about it, it's essentially an ordinal scale. So you're ranking your intensity of affect orientation, either agree or disagree, based on some kind of statement or something that's presented. Now, ordinal, but we treat it like interval data. That is, we calculate means and averages and things off of that kind of data. Now, the reason we do that, it isn't good math, but if you're an IO psychologist or you're a social psychologist, it's still going to give you meaningful data. Percentage of library budget spent on staff salaries. Believe it or not, libraries are as fully staffed as they ever were. If you go to the tech library, or if you go look at the staffing patterns there, there's as many people working there as there was 10 years ago, 20 years ago. It's just that they're no longer working with customers in person. What's happening is they're dealing with loading documents online and helping people online. That was one of the things I discovered when I went to our library, was that the people that are working as librarians are just as busy, if not busier. Statistics, what's what? Objectives, research questions, understanding what's happening with populations or describing populations. I'll go back to my own definition. Summarizing and characterizing what's happening within a group of numbers. Comparative objectives, hypotheses, inferential statistics. So with hypotheses, the hypothesis being, if you recall this from previous stat classes you had, the default hypothesis is going to be that null hypothesis. That is, you're looking at two sets of numbers, or if you're looking at some kind of pattern of numbers, there's either no difference or there's nothing going on there. So your job with inferential statistics is showing that that on the basis of random probability, there's a very, very low probability that there isn't a difference or there isn't something going on with pattern of numbers. Descriptive statistics can be applied to any measurement, whether we're talking qualitative or quantitative. In other words, if I'm looking at differences that occur, like I'm watching behaviors, I'm trying to categorize behaviors. Quick example, that based on some research that some of my undergraduate classmates did years ago, they were watching people's liquor consumption or what they were drinking, and then looking by male and female, and looking at whether they were sitting alone or they were interacting with others. So what they had was a totally qualitative research design where they were trying to say, okay, is there some kind of pattern here? Are men sitting alone more likely to drink beer, or are women out with other women, or groups of men and women are more likely to drink mixed drinks of wine? Totally qualitative, do the descriptive analysis. Well, you can actually, we'll talk later in the course, there's actually inferential statistics that you can apply for those situations where you have everything as categorical data. Offers a summary, overview, and description of data, doesn't explain or doesn't interpret. So a number of states are having primary elections this week. What they'll get out of the numbers is they'll tell you what the voting patterns were for Democratic, for Independent, for Republican candidates. Give you a summary, give you an overview of what's happening, will not attempt to explain it. And the explanation actually comes, the explanations will come afterwards from CNN, from MSNBC, from Fox News, from CBS, or whomever, where they'll look at those patterns, they'll say, well, here's why this is happening. Okay? And again, they're just looking at descriptive statistics. They're making inferences based on those patterns, logical inferences, but don't really have a whole lot of strong, at least scientific proof to back up those inferences. Now, having said that, I'm not going to tell you not to watch Fox News, MSNBC, CBS, CNN, or whomever. I think the most fun, if you've got time to watch those sources, is look at what they're presenting and see how much that is similar, then look at what they're presenting that's different, and then think in terms of which one, based on what unit, which one makes the most sense. But again, we're talking about making intuitive decisions and not necessarily making data-driven decisions. Yeah, if you're going to say something that kind of characterizes a lot of what we do in life, is we make a lot of intuitive decisions. I think increasingly, as people have feedback from social media or other, let's say, platforms that kind of measure what's going on in their lives, I think people are going to start making more data-driven decisions. I certainly do with a lot of my outcomes, or a lot of the actions I take. Descriptive statistics, well, how many, number, frequency count, percentages, deciles and quartiles. And if you haven't dealt with deciles and quartiles before, deciles are where you just take and break a group of numbers down into 10% categories, quartiles, 25% category. Measures of central tendency. I know everybody here is probably very familiar with the mean and midpoint or median and the mode. The one that we're going to use a lot for the stats we're going to be working with in here is going to be the mean, not the we aren't going to take, discuss the median more a little bit. Variability, how do those numbers scatter in whatever grouping? Variances and standard deviation, how do those, and what the variance is the average amount of scatter from the mean that numbers, pattern of numbers will produce. And the standard deviation is where we take the square root of that variance so that we can say, okay, we've taken these numbers and this is what that distribution looks like, with the idea that we're trying to see how closely it approximates normal random probability. Now, normal random probability is represented by that bell curve. You can see the bell curve, which I'm sure everybody has. That's a pattern that comes out of nature. If you were able to measure the height, the weight of everybody on the planet, you're going to get a bell curve. Same thing happens with an IQ. However, because of what's happened with human beings starting to control nature, you're not going to get a bell curve if you start plotting age. Now, when I say control nature, controlling the environment, living longer and healthier, and also, controlling our fertility rate, having more offspring or not having more offspring. So that's no longer going to fit a bell curve. The only time it probably a bell curve fit the population would be in those periods where human beings have relatively less power. So in other words, Stone Age people. I think what scares me about Stone Age people, were, if I was to live in that era, I would have probably been dead about 20 years ago. So, the average life expectancy may be mid-30s, late 30s. And, for those of you that have done any of the genetic testing, that's always fun. And then look up population groups, if those can be identified. The National Geographic genetic test does that. I think the biggest thing I got out of that was 2.5% Neanderthal, which is quite a lot when you think that, okay, those family members died off 30,000 years ago. And according to my friends, that explains a lot about my behavior. I think mostly my not being real fussy when I'm eating behavior. Graphs. We'll talk a little bit about graphs and histograms. Still very handy for representing categorical data and proportions within categorical data. Normal curve polygons, frequency polygons. It's essentially what the normal distribution is, where you put the dots down and you connect everything with a line. Central tendency, the quick review here. Mode, most frequently occurring value in a distribution. Perhaps the most unstable that it can shift, depending on what your sample looks like. Median is the one that's not going to shift. It's going to occur at the same place every time. Now, there's something I've talked about in other classes where when people that are making policy want to talk about central tendency and how bad things are doing, they'll use the median. And the example that I use in a lot of classes is that when people are trying to get funding for education, they'll go in and start talking about how bad things are going because half the students test at or below the median. And then they get the funding for their education initiative, and 3 months later they're saying, okay, everything's changed, half or at least half are at or above the median. Well, based on what that number means, half were at or above the median the whole time, half or at or below the median the whole time. Now, the point with that too is that if you have a distribution where it goes kind of wonky, where it isn't forming a good bell curve, a lot of times people that are doing statistics will default to the median instead of the mean. And the mean, just add up all the numbers and divide by the numbers, that arithmetic average. Now, with the normal distribution, all three of these are going to appear at the same point. You have a normal bell curve distribution. All three measures of central tendency are going to fall right exactly the same point. So, quick lesson here. Midpoint, you've got a range from 61 to 92, and if you look at what's happening and calculate the range here, you're going to determine the midpoint. The median number is going to be 81. So half of all scores fell above 81, and half of all scores fell below 81. And if you notice, it doesn't matter if you have duplicate numbers, you're still going to cut that grouping of numbers in half find the point at which half the numbers fall above and half fall below. Another example here, if you wanted to do this just by cutting a distribution in half, even number of scores, meaning it's going to be the halfway point between these scores, sum the middle scores and divide by 2. So 7 and 10, the median, if you're to say that, okay, this comes from the same population, the median would fall at 8.5. And this other characteristic, insensitive to outliers and extreme scores. In other words, if you have that really wonky distribution where things are kind of off a bit, the median might be the best measure of central tendency. Arithmetic average, mean is half of the sum of a set of values. So scores example here, sum equals 55, number of scores, got 6 of them there. Divides 55 by 6, you get 9.17. So the mean, and this is what's problematic sometimes with, we're doing inferential statistics, is that the mean can be influenced by external scores. Yeah, only appropriate with interval, that should be ratio, not ration. Ration data, yeah, like we're talking camping food here. Is this 4 points for scale ordinal or interval? And like I was saying earlier, with something like this, when we're doing some kind of analysis on this, a lot of times we're going to treat it like it's interval data. We're going to calculate averages because we think that calculating averages of distributions based on this can tell us something even if it's not good math. But by its very basic nature here, what you have is essentially an ordinal score. So on a scale of 1 to 4, tell me how strongly you feel about something, either agree or disagree. And of course, if you've worked with Likert scales before, most of the time, Likert scales will have a midpoint. Mode. Frequently occurring value in a set. Best if you're using nominal data. Not a lot of times where we use the mode to try to calculate some kind of differences among populations. We'll just note it in terms of, here's the one that occurs most frequently. Now, 2 years average median outcome, an old example here from census data. Census data is also real fun to play with if you're or if you're testing to see if there's differences in proportions by part of the country. You notice what they have here, median incomes listed here. And the reason for that is if you ever look at the distribution of income in the United States, it's no longer a bell curve. Actually, we have in the United States, we've got something where it's an extremely right skewed distribution. Because what often gets noted in the news is that there's about an upper 2% of the population that has, depending on whose estimate you want to use, either 75 or 90% of the income of the wealth. In other words, if you're going to calculate what an average income is, that might not even be the best measure. Now, I'm going to say, too, now with how things are going and how the wealth of the upper 1% has increased, I don't think the median is really going to be useful anymore either, because it's going to give you kind of a biased example and make it look like people's incomes are higher than what they are. And that's one of the concerns I have, too, when they calculate a lot of this stuff is they'll say, well, the average income in the U.S. rose by 5% or whatever. Well, did it rise for most of the people, or did it just rise on the top end? Or if they say something, income has gone down, does that mean that the people at the top lost a little bit, or does it mean the people at the bottom lost a little bit? So can't really tell from these numbers. So the normal curve, the bell curve, and again, this is something that comes right out of nature, that if we go out and measure anything that's perfectly randomly distributed in nature, we're going to get that bell curve. And again, it could be the height of all the people on the planet, the weight of all the people on the planet. And I think even within population groups, you might find differences in terms of the range of the variance within a group, but you're going to still see that bell curve. And when we're doing inferential statistics, there's a concept called sampling distribution of the means. It's based on this idea that if you repeatedly sample a distribution, you should have a normal distribution of values that would cluster around the mean. And that's going to become conceptually important when we start talking about t-tests and some of the information. Now, hopefully, you know how to do these things. And what we can do in here is we'll talk about the conceptual underpinnings, which is kind of useful if you're going to go out in your careers and you're going to be doing things like program evaluation or criterion validation studies or organizational climate surveys. Make sure that if you're not going to sample a whole population, how do you make sure that you've got a representative sample of population, not in terms of how you define it, only in how you define that population, but in terms of how you sample within that. And what I was saying before, bell curve, mean, median, mode are all going to fall in the same place if it's a perfect bell curve, perfectly normal distribution. An example here, you know, your theory is wrong. Now, if you've done anything with correlation or regression, you've done something where you try to fit a line through some observations, and that distance between the line and the observation is what's referred to as residual values. This example here, you've got this residual value sitting right out there where it's not even close to one. Now, most of the time, if let's say you had a real pattern like this, we had a straight line and stuff was falling fairly close to the line. You have one that's lying out there somewhere. It's throwing things off a little bit or a whole lot. If you can identify how that's different, you can take that observation out of the data, or go ahead and take that observation out of the data, but you document it, you let everybody know. So that way, if somebody afterwards wants to take a look at the analyses and determine whether they are or not confident in your analyses, you've done an ethical job in terms of what you're doing. Normal curve, mean, median, mode, all in the same place. And again, if you picture this from the shortest person, smallest person on the planet, to the biggest person, you're going to get this. There's actually a version of this that you can do if you want to flip a coin. So if you flip a coin 100 times, the greatest probability is that you're going to get heads or tails, but there's also a certain probability that you're going to get, let's say, heads 10% of the time and tails 90% of the time, or tails 90% of the time and heads 10% of the time. And again, what we're looking for when we test, the hypothesis testing, is whether or not something falls way outside of that category. Few distributions, a lot of the distributions we're going to be working with data are going to be skewed. In this case, we have what's called a right skewed distribution. And basically what you have here is more of the observations falling on the low end. So let's say you're going to go to some poor community, and you're going to take the average household income and calculate what that distribution looks like for that community. Well, if it's an impoverished community, it's going to look kind of like this. If it was a wealthier community, that this would be the other way around. Extremely hard tests, which would also be an example of this, where grades are going to be more towards the low end. Or an easy test, it would be the other way around. So the mode is smaller with a positively skewed distribution. The mode is going to be smaller. Let's say the numerical value is going to be less than the median. So here's the mode. Here's the median. Okay, so this relationship exists because the mode is the highest point on that graph, of course, part that sticks up if you want to put it in plain English. And the median is also going to be at that halfway point. Now, the other thing that's going to happen with that positive distribution is we said that the mean, median, and mode fall in the same place with a normal distribution. What's going to happen with this is here's going to be the median, here's going to be the mode, and the mean is going to be right in there. If you kind of picture that, this area here is going to be equal in terms of the amount of volume that it takes up as this area over here. So not only can you prove this mathematically, but you can also do it just by drawing out it works with graphics. Now, easy test. I'll give you a better example of this. This is what a grade distribution should look like in a grad class, right? Because if you think about what was required to get into grad school, you had to have good GPA, decent GRE scores, and so consequently everybody's been pre-screened, so we don't exactly have the normal population. We have is people that should largely be from the right tail of the population. Or again, easy test in a class or a test for which everybody's prepared, you could get this kind of distribution. The other thing I could say about this too, for people that do training and development, if you're testing people before and after training, what you're hoping for after training is that, let's say that went from being like a negative, a positively skewed distribution before training in terms of people's pre-test scores, they receive the training, and then it becomes a positively skewed distribution. So negative, the order of the measure, acceptable tendency would be the opposite, which means the mean being small and the median, which is smaller than the mode. That's all that's drawn here. Mode, median, and mean. Now, variability, differences among scores, and some of the things we talk about dispersion, that is how much are things scattered from what's considered average or the middle of that set of numbers, the range, what's the highest or the lowest values within that group of numbers, and the variance and standard deviation. Well, we try to calculate average amounts of spread or dispersion from the mean. Usually with interval or, okay, I need to get in there and correct that. Interval or ration. Now, we're going to ration the data here, so I'll stay, pay attention because here comes a little bit of data. Okay, so that should be ratio data. Standard deviation, and again, it's the idea of how much on average differences are from the mean. And then what we can do with the standard deviations, we can take each individual score and report how that individual score compares to the whole group. So again, another example, IQ tests. You know, we don't do things like saying, okay, the person with the IQ of 160 is twice as smart as the person with an IQ of 80. What we do is we say that, okay, about 68, a little over 68% of that population is going to fall between plus or minus 2 standard deviations from the mean. So with the Wechsler Adult Intelligence Scale, basically what you're saying is that 68% of that population is going to fall between an IQ of 70 to 130. And then 95% of that population between an IQ of 55 and 145. And again, that's how we're going to interpret the difference. This measures how much subjects differ from the mean of the group or how they compare on average to the group. The more spread out, excuse me, that the subjects are from the mean, the larger that standard deviation is, and sensitive to extremes or outliers. Now, within a whole population, we'll have enough to fill in. We don't really say we have outliers. But when we're dealing with samples, a lot of times we have outliers. So this is what I was talking about before. If you're going to look at something where you have normally distributed population and then where those groups fall. So 68% is going to be plus or minus 1 standard deviation, 95 plus or minus 2 standard deviations. By the time we get up to 3 standard deviations, we have 99% of the population. And a lot of times, if you look at what we're looking at or what we analyze, we don't, if we capture 99% of the population, we're happy for purposes of our own research. The only exception to that is if you're like looking at, let's say, pathologically, in clinical counseling psychology, looking at pathological populations, or if you're doing something where you're looking for super. Inferential statistics, comparison across variables, is a relationship between one occupation and the reason for using a public library. Hypothesis testing. So, for example, or whether or not people do use a public library. So can we determine by looking at library usage, and if we have people categorized by accountants, engineers, registered nurses, retail salespeople, then we find differences within those groups in terms of what proportion uses the library on a regular basis. Now, where this gets more interesting, if you're going to use that library as an example, the library here in town, and certainly the library here on campus, do a lot of online visits. So if anybody really wanted to look at this and see who was using the library, you probably would be able to get the data electronically. That idea that ultimately science doesn't prove anything. Significance level is going to be the point at which we're going to say that, okay, we're going to conclude that something is happening with this set of numbers and it's not just random. In other words, we have some kind of pattern with this example where it's less than 5% probability. That has been the rule of thumb with psychology and the social sciences going back 140, 50 years now. The social science is going to deviate from that. It's going to be from two of them. Sociology and economics sometimes will use a p-level of 0.1 or 10%. We're dealing with individuals. We're looking at individual behavior. It's 0.05. And we're saying that, okay, the probability of this just being random is less than 5%. But again, science doesn't prove anything, so we're saying, okay, there's also just under 5% probability that what we have here really is just a random pattern. So what do we do with that if let's say we're doing multiple studies, or we're doing studies where we can't say we've proven anything, and that significance level comes up at just under p equals 0.05, and we'll best way confirm something or try to confirm or support something, just do multiple studies, and if it keeps coming up as 0.05, what you do is you multiply that p-value by the p-values of the other studies, so 0.05, 0.05, 0.05, and if you calculate that out, it's less than what 0.00125. If I can do that right now. In other words, the probability goes down if you replicate the same study, even if the p-level is the same study. Now, y'all remember this, I hope. If not, we're going to go through this again, and we'll refer to this frequently, the idea that science doesn't prove anything. And any study that we do is going to have a probability that we've created one of these two types of errors. So the type 1 error, we reject the null hypothesis. That is the idea that there isn't a difference there, or the variables aren't related, or there's no correlation. We reject that, say that we think we have something when in fact we don't have anything. And then type 2 error, we fail to reject the null hypothesis when there really is something going on. So we reject the null hypothesis, or fail to reject, we retain the null hypothesis when it's false. So false positive, false negative. Anybody that's ever had a strep or mono test, I think it works the same way, I understand, with the testing for cancers or the testing for HIV or hepatitis, that a lot of those tests, especially with some kind of disease that could have severe consequences of being somewhat lethal, is they'll set those tests up so that they create this one, a false positive. Because then what they can do is they can retest with a second test, and if it comes up as being negative, well, better safe than sorry. The other thing that happens with respect to the kinds of stuff that we do is if we reject, if with medical testing where you're testing for diseases or cancer or whatever, a false negative is going to be worse than a false positive. I guess we could say this the same thing with like a pregnancy test too. So false positive is going to be better in some cases because then to get prenatal health or give up drinking or smoking or anything that could harm a fetus, right? On the other hand, with the stuff that we do in IO psychology, false positive sometimes can lead us to spending money that concluding that something is working when in fact it doesn't. Could lead us to spending lots of organizational money on something that doesn't work. The other hand, you fail to, you get the false negative, you can always take a look at it later, and if the data come up differently, then you can make a decision in terms of whether that second study is false positive, or if it actually confirms that whatever you were pilot testing would actually work in that organization. Probability, inferential statistics to make decisions. We can, report probability that we have made a type 1 error, and that's what that p-value is. So p equals 0.05 means there's a 5% probability that you were wrong, that there really wasn't a difference there. By reporting the p-value, we can tell the reader what the odds are that you might have been incorrect, and then the reader can make a decision in terms of how much confidence they want to have in your study and in your results. So for example, if you report that your results were significant at 0.05, that is, there's only 5% probability that you're wrong. You report them at 0.001, there's only a 1 in 1,000% probability, 1/10 of 1% probability that you're wrong. That might be, those might be results that people would have a little bit more higher confidence in, especially as a first step. Okay, some of the particular tests we could use. We'll actually talk about some of these. I've got a reports, I think it's like the second last week of the quarter, talking about some of the alternative types of statistics. Now, we don't usually give a lot of coverage to these types of statistics because I think the idea is that ordinary least squares, that is the statistics based on normal distributions and working with means, are the ones that are more difficult to understand, so we don't give as much coverage to these, but I promise you, you'll get coverage on these in here, and what we'll apply these to later in the quarter is we'll look at adverse impact and we'll look at test size. In other words, test whether people in one group were more likely to pass or do well in a test than people in another group, as a way of determining whether or not we are looking to see whether or not we have to look at the test to see if it's a biased test. Now, quick example of test bias, and if you're in PSYC 543 tomorrow night, you'll get some exposure to this. A bias test is one where two people of equal ability achieve or acquire two different scores on that test. It's a little bit different than saying, okay, if you have two people that score differently, it could be real differences in ability. If, even if it was something like an engineering test and the lower scoring person was female and the higher scoring person was male. Now, it could be a bias test, or it could just be differences between two groups or two individuals. The numbers aren't going to tell you whether it's between group differences or whether it's biased, but the numbers will tell you, hey, something is going on here, you better take a look. There's some consequences, or problematic consequences, with respect to who does or does not pass the test. Bottom line with that is, you want the test to be unbiased, and you want the test to be the cleanest, most accurate measure of whatever it is you're trying to measure. I'm guessing if you had PSYC 300, you might have talked about chi-square, where you're looking at groupings. Real quick example, I'm going to draw one on the board over here. And I'll rotate the computer slightly. I don't know how well this is going to show up. It looks a little bit light. But anyway, chi-square, a quick example, 2x2 contingency table. Have men and women as one grouping, and then voted Republican or voted Democrat as the other grouping. Now, typically what we find is, let's say if it was going to be perfectly equal, if there wasn't a difference between men and women in terms of how they would vote, then you would find, let's say this is 100 people, you would find 25 in each group. That would be just, that's what random, the highest probability result is randomly distributed. However, you could get something where it isn't completely 25 in each group, which would still be perfectly random. But typically what they find is that a higher proportion of men, based on probability, a higher proportion of men are more likely to vote Republican, and a higher proportion of women are more likely to vote Democrat. So in other words, you have something where it might be like 40-10 here and 40-10 here, okay, which deviates a lot from 25-25-25, and consequently you would have to include something other than just normal random difference. And exit polling, they could kind of confirm that a lot of times. Even if you have people coming out of the same household, there'll be some differences based on which issues people are concerned with or where they fall with respect to beliefs about issues. Something called the Kramer's D, or the P coefficient. This is going to be a correlation. We have two categorical variables. Certainly, affected by the number of cases, where the larger the number, the easier it is to find statistical significance. We'll discuss an article by Paul Neal that talks about this, how when the numbers get big enough, even little tiny differences come up as being statistically significant. I think the relevancy for us in applied psychology is that small differences or ultra small effects aren't really meaning for us. We need effect sizes where it has some kind of practical. Two-tail distribution, one-tail distribution. We'll go into this in a little bit more detail. I know you probably covered this in Psych 315 and 415 if you've had stat classes here at campus. But, you know, are we going to set things up so that the hypothesis or the findings go either up or down, or do we have strong theory we think things will only increase or decrease and decrease one-tail distribution? The difference between those two is the one-tail distribution is going to make it easier to hit statistical significance as long as the results linear in the hypothesis direction. Correlation, degree to which two variables are related, that is how degree to which how much one variable changes with the other variable, can range from -1 to +1. Now, negative correlations are just as important as positive correlations. All negative correlations mean is that the variables are moving in opposite directions. So in other words, if one variable goes up, the other variable goes down. A quick, maybe kind of cheesy, lame example. As the temperature goes up, the weight of the clothing that people wear goes down. As the amount of exercise that people engage in increases, weight goes down, things like that. So again, inverse relationships. Now, when it gets close to zero, that's when we say, okay, there's really nothing going on here. And we can say with a correlation coefficient, it is two tests. It's that measure of association between variables, and it's also a test of statistical significance. So we can look up what that correlation, what the probability of getting that correlation with the number of observations is, and number of observations are, and make a determination in terms of whether or not that association appears to be random or it appears to be non-random. Now, the last term here, Spearman's rho, form a correlation where at least one of those variables is going to be ordinal. So the example I was giving you before, temperature goes up, weight of clothing goes down, exercise increases, physical weight decreases. Okay? Those are going to be interval units. And actually, if you're going to quantify exercise in terms of number of minutes or hours spent exercising and weight in pounds, those are going to be ratio variables. Well, we can also have situations where we're correlating two rank ordered lists. So for example, if you're watching the decathlon and the Olympics, the people, the order in which people finish the swimming event, does that correlate with the running event or something? We can go triathlon with that, right? Biking, running, and swimming. The people's relative orders correlate. Let's say you're, I don't know if they do this anymore. They used to have class rank within classes. So in other words, the person that had the highest score on something, the lowest score without recording the numbers, but just rank ordering people, did, you know, the rank order on test one correlate with the rank order in test two. So the people that haven't had enough tests or you can't get enough of this stuff, again, what I'm going to try to do with y'all is we'll move through some of this basic review stuff fairly quickly. And then next week sometime, well, I might even get to it, maybe at the end of this week, I'll send out a form and have you all state goals and objectives, what you want to get out of this class, and then tell me a little bit about what you see yourself doing either a year after graduation or 5 years of graduation. Tell me about your career target, and we work on those kind of statistics and that kind of math with this class. P-test, 2 sample means, or 2 different group means, pre-test, post-test. So you're doing training and development, pre-test people, deliver the training, then give them a post-test. If it's 2 different groups, who needs the Microsoft Excel training the most? You have to make a decision, test, and see if there's a difference between the accountants versus the engineers. And whoever scores lower, and assuming that that lower score is different than just normal random fluctuation, that's the people who get the training. Easiest way to perform research design. Right, 2 different groups, see if there's a difference. Well, a lot of the stuff that we're going to be doing in our careers, T-test is going to be maybe good for a pilot study, but then we'll have to get into analysis of variance. And analysis of variance, if you're calling it that, is just like t-test, only we're going to extend on that logic. Instead of looking at the difference between two means, we'll look at how the variation within groups differs, determine whether or not those groups are the same, or whether those groups are different from each other. And then regression analysis, I'm thinking if you had 415 with Mitzi, or perhaps Jeff Walsick, you got into this somewhat. You know, both of them have some really good real-world data that they can help people practice on. I've used that in the 415 class. We'll get back into this a little bit and talk about how you do some of this stuff. We'll make it more specific for workplace settings and how you apply this in workplace settings. Analysis of variance. The idea is that this is going to be an extension on t-test. Now, part of the reason we do this is every time you run a t-test, all those, let's say you do multiple t-tests, what you have to determine the ultimate level of statistical significance is you add up those p-levels. What ANOVA does for you is it controls for the number of comparisons you make. So that's one advantage of it. The other advantage of this is that if you've ever done this with statistical software, it's so much easier to put data from, you know, two or more groupings, you know, at two or more levels into the statistical software. Just run one test and see across all the different groupings if there's any differences that you need to get back in and look at, or if nothing's going on. So in other words, ANOVA becomes a real simple way to answer multiple questions with the same analysis. Now, what I was saying about regression and correlation is that we have two things that's going on here. We're looking at whether or not there's an association between or among two or more variables, and we're also determining whether or not that relationship appears to be chance, just random, or something non-random going on. Well, the other thing we do with this is we look at the strength of that relationship. So with regression, examines the association from a different perspective, yields an equation that uses one variable to explain the variation from another. That is, with the correlation itself, we're doing is saying, okay, how strong is this relationship? And with regression, we're taking that same statistical method, we're deconstructing or rearranging the equation so we can put in any value of one variable and say within given limits what the valuable of the other variable is going to be. The other thing we do with regression too is we also will test what are called the slopes or the regression weights for statistically significant differences, but also to say, okay, this is strong or this is a weak relationship. Yep, more tests. And if you can almost see what's going on here, you recognize I stole a line from Office Space, right? Yeah, that'd be great. Yeah, whatever, lumber. Multiple regression examines differences between a dependent variable and multiple independent variables. We put variables in what are called linear composites so we can see how much each one of those variables is contributing to change in maybe a target variable, an independent variable. Sometimes we turn these things into what are called path analyses and causal models. We're looking at how each variable influences the other variable without necessarily designating one as being independent. Now, stepwise multiple regression, this is one of the defaults in SPSS, and we should be able to do this in JASP. And you know, predict the valuables. It's been a long day. Basically, what we'll do is we'll kind of put the variables in and we'll assign them values or weights based on which was the highest, which one was the lowest. And typically with these types of formulas, you're going to find variables where there's some overlap in terms of their association with another variable. So you have to make a decision in terms of which variable is going to get that overlap, or you're just going to pull that overlap out of the equation. And if you've worked with this before, you're going to recognize what I'm talking about, the semi-partial and partial correlation coefficients. We'll get into that and take a look at how that works and the logic and rationale behind that and when it makes sense to do that. Parametric versus non-parametric statistics. And again, if the statistic is based on a bell curve and it's based on looking at differences from a mean, that's going to be a parametric statistic. So require interval or ratio level data. Now, the time we're going to violate that, again, with things like Likert scales or attitudinal scales, we have strongly disagree and strongly agree. Again, if you're going to be somebody from the math department, you're going to say, wait a minute, those aren't interval or ratio, certainly not interval, that's ordinal data. But we're going to treat it as interval data because differences in terms of people's affect orientation, whether strongly agree, neutral, or strongly disagree, can tell us a lot about how people think and how people feel, and we can make data-driven decisions. Even if you want to say technically we're doing this, we're kind of violating basic mathematical assumptions. Well, anyway, parametric statistics assume that we're using stuff that's normally distributed. Okay? That is, the data is going to either be a bell curve or close to a bell curve. Now, when we get to talking about analysis of variance, if you discussed the assumptions before, the statement is usually made that ANOVA is relatively robust with respect to violations of the assumption. So you can have something where the data, skewed, left skewed, right skewed a little bit, and it'll still produce a useful result. The thing is, the more that data violates assumptions, the less likely it is to come up statistically significant. So for most situations, you're not going to get yourself in trouble if you violate assumptions. Matter of fact, what used to happen with SPSS is that if you had data that did fit the assumptions, SPSS would give you a warning window with red font saying, data violate assumptions. Now, we get to working with some of the multivariate stuff in here. You're going to see just that happen, where if you put data in where it can't be analyzed using that method, SPSS or JASP or R will let you know that what you're doing, or the data aren't amenable to that, so consequently it's not going to calculate anything. Now, non-parametric statistics, no assumption about population distribution. Typically less powerful and often need large samples. Let's focus on this word right here. What does power mean? Power, for our purposes in here, means that the statistics have the ability to reject the null hypothesis. In other words, if you're dealing with inferential statistics, with parametric statistics, and assuming your data are roughly normally distributed, you're going to have more power, greater likelihood to reject the null hypothesis. Non-parametric statistics, not always the case, that you have to have bigger differences in groups or patterns or frequency counts before you can reject the null hypothesis. So less powerful. Now, power doesn't always mean you're going to be right. It doesn't always mean you're making the correct assumption. If I take and raise the alpha level up from 0.01, which I'm saying, okay, I will accept the results if there's only a 1% chance of this just being a random pattern, move that up to 0.05, where you're saying it's a 5% chance of being a random pattern. You've increased power. You've also increased the likelihood of making a type 1 error, but you've increased power. You've increased the possibility of rejecting the null hypothesis. There's going to be other ways that we'll talk about in here too, about how to increase that power without increasing the likelihood that you're going to create a type 1 error, or produce a type 1 error. On the flow chart, the week after next, we'll talk about the appropriate statistical technique. So, appropriate measurement scales to use. You need something where it's going to, does it really measure what it is you say you're measuring? Is it ordinal, or nominal, ordinal, ratio, or interval? The intent to characterize respondents or draw inferences from a population, descriptive statistics or inferential statistics, and did you identify the right population before you started the research? The level of significance of focusing on one-tailed or two-tailed distributions. What I typically do if I'm doing something in a workplace setting and I don't have strong theory is I will use the two-tailed tests just because they're more conservative. Because basically what's happened with that two-tailed test is you've taken that region of rejection in the distribution. That is the region, point at which you're going to say that something is or is not statistically significant. You divided it to, and you put half of that one tail, half of the other tail. Again, applied research, sometimes it's a better route. If you have something where you're testing previous theory, it might make sense to use, and you think that something is either going to only increase or decrease, it might make sense to use the one-tail distribution. Whether the mean or the median is better to characterize the data set, we'll do some activity in class, and by in class I mean we'll either do it in class or send it out as out-of-class activity to have you plot some data, take a look at that distribution, and make recommendations in terms of whether you use the mean or the median. Whether the population is normal. Now again, with a lot of stuff that we're looking at, we're going to have normal populations. But there's going to be cases where the population is going to, or the distribution is going to be somewhat skewed. I'll give you a quick example that I'm really familiar with from my work, is if you're looking at distributions on selection test scores, typically you're going to have a left skewed distribution, because if you have a recruiter working for you who's supposed to be sending the best qualified applicants to take the test, you're going to eliminate a lot of people who will be at the bottom of the distribution. The other thing I can say that happens too is when you put some kind of vacancy announcement out there, people kind of pre-screen. So people will look at that vacancy announcement and think, okay, what's the probability of me actually getting this job? What's, how well will is my skill set fit this job? Are they paying enough? And all those decisions will kind of cause people to self-select in or out. And what you'll end up with is the left skewed distribution. That is, the people that are more likely to have the skills and more interested in that job are more likely to sit for the test and have higher scores and have it produce a skewed distribution instead of adult. Number of independent, we could call experimental or predictor variables that the evaluators manipulate and presumably change and influence the dependent variable. Now, a lot of the research that I've done, a lot of the research that Tani has done too didn't involve manipulating anything, but did involve looking at certain things like demographic variables or educational variables, or in Tani's case, looking at things like perceptions of justice in the workplace and commitment in the workplace. In other words, he didn't manipulate perceptions of justice, but he wanted to take a look at whether or not perceptions of justice within that workplace led to higher levels of commitment. So justice, perceptions of justice, that measure becomes the independent variable, and commitment becomes the dependent variable. Again, nothing manipulated, but one is still used as the experimental or predictive variable. Now, when we do that, we have what's called quasi-experimental research. So for most applied psychologists, there will be, we'll be doing quasi-experimental research. We're not really going to go into manipulating. The times I have manipulated stuff has to do with, a lot of times with changing something in the workplace environment or training. In other words, if I want to see whether training is going to work, take my pre-test, deliver the training, and whether or not people did or did not get the training becomes my independent variable. I actually manipulate something and then do a post-test and see if something changes. That would be close to being a true experiment. Now, to make it a really true experiment, it basically assumes that you're going to take a random sample. The example I gave you with the workplace or doing research on tech campus, we can label that as being a convenient sample. That is, you did your research with the people available. You don't know that, always know that the people who are available were representative of the whole population who you want to generalize. So, parametric or non-parametric statistics. This idea of looking at what the results of your research are going to be. Do they cause people to change their behavior, or conclude that something works when in fact it doesn't work, or could conclude something doesn't work when in fact it does? So you're also taking a look at this in assessing which is worse, having that false positive or having that false negative. Type 1, possibility of rejecting a true null hypothesis. That is, you conclude you have something when in fact it's just random. or the possibility of accepting that null hypothesis when in fact there was something there or something really different. Okay. So let's see, how are we doing time-wise? We're at about 7:12. I've got one more thing I want to roll out. That is, let's take a look at that JASP website. Okay, so if you go to Google, you go to Bing, you go to Yahoo, just type in JASP, and it'll bring up this link, jasp-stats.org. Now, this is a little bit fuzzy, but if you look at this, this kind of looks a bit like some of the interfaces you might see with Excel. And right here, the download. And kind of what I've noticed is that it doesn't take up a lot of space on your SSD or your hard drive. And let's put the download over there. So here's what I think is really cool about this. It's free, and you can put it on your Microsoft device, or you can put it on your Apple device, or for those of you that are hardcore old school programmer types who like simple operating systems, there's a Linux version. Okay? I think Linux is kind of cool if let's say you have an old computer that's kind of slow, upgrade it with Linux, and assuming you're not trying to run Windows apps with all the graphics and animation that they produce, Linux works just fine for using computers as tools. So you got that old whatever the Dell with the dual core, from 10 or 15 years ago. I'm guessing for you all that might mean like when you were kids. Just sitting around doing nothing, you might want to use it as a Linux machine. It's certainly Linux. Linux will make that machine seem like it was as fast as when it originally had Windows XP or Windows 97 2003. Easy download. Once you download it, it opens up, and you're good to go. And then it just you just put it with your program files. Icon to the desk, and it opens up really just super quick. And then support. What I found cool with this is if you have any kind of problems, get a hold of people, and a lot of times you're linking up with volunteers, but people will get back to you with answers. And then, with respect to materials, now when you look at this, it's going to be fairly simple, but there's books and papers out there. My recommendation for using this is if you're not comfortable with SPSS, if you really want to try to learn this pretty quickly, go to YouTube. Lots of good recent videos on YouTube in terms of how to operate this. I will stop right there for the night. I'm going to put up a discussion post for questions. So if you have any questions based on tonight's presentation, feel free to send them to me. What should happen in theory with my workload is that Mondays and Fridays I don't have anything scheduled. The university closes at noon or 12:30 on Friday. So if everything gets all backed up or get too jammed up work-wise, longest I'll delay before I get back to is going to be like a Friday morning or something like that. So in terms of where to go from tonight, I'll get the other presentations put up and I'll get that individual plan of study or individual development plan sheet out so you all can take a look at that. Get the textbook. I have the fourth version of Nolan and Heinzen listed. I'm going to say that you could get any recent version of that of Nolan and Heinzen, and since there's only a total of, including me, there's only a total of 4 of us in here, and there's going to be subtle differences in where stuff is placed in those books, but they're going to have the same content. So my recommendation is, if you don't already have one of those books, get whatever you could get the cheapest, either off of Amazon used books or eBay or whatever source you use. Now, there's another text we may end up using in here. And if that happens, I'll let you know how to get it. It's the Green and Salkind book, the Green and Salkind book that has a lot of examples, especially regression examples, and also comes, this would be like a used book that would cost you maybe $4 or $5. off of Amazon. But the other thing I could probably do too is just list out the exercises and provide you with the data, then we can work through all that. So anyway, it looks like Donovan is the only person that's attending live. So I'll get the video posted. And again, if you can't make class, take a look at the video. If you have any questions about that video, just send an email or contact me. And I'm forgetting anything here? Okay, can't think of anything I'm forgetting here. Get the book, get started with the readings, and if stuff is too much review, or if it's stuff you already know, let me know, because then what I'll do is I'll work with you individually to make sure you're getting a sufficient level of challenge. Because the bottom line, given the kind of opportunity we have this summer, the bottom line with this class is let's use this to develop your individual skills as applied researcher and applied IO, or applied researchers and applied IO people. Any questions, comments, or concerns? Again, send them to me. Otherwise, I'm going to, let's see, I'll wish Donovan good night in person, and hopefully get this up so the rest of the class can see it.